Indeed, it's a pleasure to start off this day. You've learned a lot about electronic structure calculations in the past week. I'm sure you've tried to do electronic structure calculations, and if you tried it on more than a couple of atoms, you will have discovered that it's very slow. So of course, this is relative, right? So one person's slow method is another person's amazingly fast method, and I think one just has to get used to this this idea of scaling. There's always a problem that is a materials problem or a problem of chemistry that is interesting, which we can't do with sufficient accuracy. I was reminded of this a while ago when I was talking to some quantum chemists, and I discovered that the electronic structure method that was my ultimate gold standard, that is the most accurate method that I could never do for more than really a couple of dozen times, was their very fast method, with which they did sampling in order to gather configurations on which they did their really, really accurate method, which I've never heard of. So these things are always relative. In my talk today, what I want to tell you about is how we use machine learning to try and bridge some of these, jump over some of these gaps of speed. So the talk is in sort of roughly three parts. I'll tell you about how to fit functions. So that is the way we're going to jump through and speed things up. We're going to fit functions in many dimensions, and I'm going to show it to you through the example of Gaussian process regression, but I'll point out along the way that there are other formulations of the same problem. Then I'll tell you a little bit about descriptors, and the one that sort of came out from my group, which is called SOAP, which we think can solve a lot of these problems in materials modeling. And then I'll give you examples ranging from water through tungsten, iron, carbon, more materialsy things, and maybe at the end I'll just touch on, go back to organic molecules again if there's time. So essentially machine learning is function fitting, mathematically speaking. But that's not how you would discover it. And certainly mathematicians have been fitting functions for a very long time, and you can find out about splines in elementary textbooks, but you have to work hard to see machine learning in that form. So, and that is because machine learning is how to do function fitting in very high dimensional spaces, which are very hard to think about. So there are sort of two ways of doing it. If you get examples of inputs and outputs, so something from the domain of a function and something from the range, so y belonging to a certain x, then and you try to fit the function that you're getting examples out of, that's called regression. And that will be the topic of this talk today. But there's another kind of machine learning when you only get examples of the domain. So imagine a probability distribution in a very high dimensional space, and instead of telling you the probability density at certain places as examples, I'll just give you samples from the probability density. Right? I draw samples. They don't come with a scalar function, with a scalar number. I just tell you, here's an example, here's another example. And your job is to reconstruct the probability distribution. So in this high dimensional space, when you're getting in places where you're getting a lot of samples from, the probability is obviously high near there. That's a much, much harder task, and it's called density estimation, or probability density estimation. And we will not be concerned with it today. So in many, many cases, and I would say in the majority of cases where you meet the concept of machine learning, and this is how really it grew up in the last 10 or 20 years, is when the function that you're trying to fit is really unknown. You have no way of, no algorithm to computing it. So for example, if I show you an image, is it a face? Maybe it's just white noise, or maybe it's a car, right? But this function, which tells you it's 1 if it's a face, it's 0 it isn't, on the space of images, which is a high-dimensional space. If you take 1,000 pixels by 1,000 pixels, that's a million-dimensional space. No one has an algorithm to compute that function exactly, right? So that's an example of machine learning, learning from examples. I can give you a lot of examples of faces, and you're trying to construct a function where there was no function explicitly before. Here's another example from more closer to material science. If I give you a material composition and I ask you whether the resulting material is a superconductor or not. Again, we have examples. There are examples of superconductors at some temperature, or I can give you a temperature limit and say, is it a superconductor above that temperature? But no one has an exact way of computing that function. There's another way of using machine learning, and in fact that is the topic of the talk today, is when we do know a function that we're trying to approximate, it's very, very expensive, and hence my opening remarks about electronic structure calculations being often very much more expensive than how we would like. So in that case, there's another word for what we're trying to do. It's called surrogate modeling. So we're trying to build a surrogate function that is like the expensive function, but much cheaper. So for example, if I give you atomic coordinates, then one can compute the DFT total energy. And maybe you've done that last week. Perfectly possible, just takes the computer. But if I give you 10,000 atoms, and I want to do molecular dynamics, so I want to compute this function 10 million times, and I give you a laptop to do it, you're going to struggle. So the question is, should you just write a grant proposal for a bigger computer, or is there something else we can do? Can we take this well-known, very expensive function and construct a function that is somehow approximate to it, maybe not everywhere, but in places where we care, and is much cheaper? And that is that's the way in which, that's one of the ways in which machine learning has been used in the last 10 years, or attempting to be used in this field, and that's what I do. That's what I'd like to tell you about it. Of course, people have tried to compute materials properties cheaply for a long time. So force fields, functional forms that approximate some version of the total energy of a system have been known for many years, or have been written down for many years. So here are some examples. Most of you will have heard of the Lennard-Jones model. It's a pair potential, originally written to approximate the van der Waals interaction, but people have used it as a very cheap surrogate for materials modeling for, I guess, every kind of material that there is. Just the sum of a pair potential here with V2. For Lennard-Jones case, some particular functional form, you can derive a different functional form from the radial distribution function of a liquid, for example. That's a well-known technique, and so on. It doesn't work for many covalently bounded materials like carbon, silicon, more sp bonded materials. So people have invented other things, adding angle terms, for example. Here's a spring constant k, here's theta ijk, the angle between every triplet of atoms, and that theta 0 is the angle that you know well the material is trying to achieve at 0 temperature, let's say 109 degrees, the tetrahedral bonding. And so you add a penalty for deviations from that, and that's an approximation of the total energy. Not a very good one. Then there are many others. So embedded atom models are very good for metals. You take a density that is a pair that is just depending on the distance between atoms, but then you sum up all the densities at an atomic site and you put that into some embedding function phi that is nonlinear, and that gives you a rather good model of FCC metals. There are bond order potentials, and then there are very sophisticated things. One of the best potentials for even materials and organic molecules out there with a long history is called ReaxFF. It's basically an attempt to gather everyone's attempts in the past 3 decades and try to cook something up with many, many parameters that approximates the real potential energy surface. So one thing I want to draw your attention to on this slide, because we will return to it later on, is that it's something called representation. So the atomic coordinates of atoms are 3 vectors in 3D space, and how we transform them or represent them before we plug them into a function is called a representation. But when you think about these functions, usually you don't think about those steps separately, right? So you don't take the coordinates, transform them, and then plug them into a function. You just take the coordinates, and these functions are evaluated on them. But actually, inside these functions, there are representations. So here, the list of all pairwise distances is a representation of atomic coordinates, and you plug them into a pair potential. The reason this is interesting is one can ask, before you think about a pair potential, just the fact that you transform the coordinates into an unordered list of distances, does that involve an approximation? Have you thrown out much of the accuracy that you can obtain by doing that? The answer turns out to be yes. But that if you don't think about these representations separately from the functions, you don't get to think of that question. You can ask the same question for the 3-body potential, and you might say, oh, that has a lot more information in it. It has information about angles, which is true. But it's also unordered, right? The angles in this list have nothing to do with the distances in this list. So you don't know, the function doesn't know which angles belong to which distances. And that's, again, something we can think about before we do any fitting. So the real problem with these fits, with these functional forms, is that they're not correct. So these are not the functional forms of the real electronic structure potential energy surface. So this means that anything you do in this, like this, will have limited accuracy, and you can't easily improve them. You can find the best pair potential, the best 3-body potential that fits your data, and the model still doesn't work. There's nothing you can do within that approach. So what we're trying to do by using machine learning is to have a potential that is given by quantum mechanics, not just based on. Okay, so there is a quantum mechanical potential energy surface out there. For example, a DFT one. Can we construct a scheme, a framework in which we can approach that systematically? I want to broaden out a bit and talk about all the different ways that people have thought about force fields, because I think machine learning will bring them together. So the first type many of you will have heard of are biomolecular force fields. In fact, they are the ones who use the words force field most often. Here are some examples: amber charm, amoeba, Gromax, and so on. And they are very good within the domain of application. They're very good, have very good transferability. So you fit them to gas phase molecules and very short peptides, so pairs of amino acids, triplets perhaps, and then you use them to simulate entire proteins. And what that relies on is that the potential energy of these small molecules, as you stretch bonds and as you rotate around these single bonds, they do not change very much when those molecules are in a long chain. And that's the experience. Of course, the forefront of that research is trying to push the accuracy, but these guys have a lot of the accuracy that they want. That's in contrast to materials models, which need to be reactive. So models for solid state systems, carbon, silicon, I've mentioned before, but also metals. You want to break bonds. Here in biomolecular force fields, you can do a lot of science without breaking bonds. But here, it's all about breaking bonds, determining melting points, surfaces, reconstructions of different surfaces, perhaps motion of dislocations and point defects are what is interesting. Here are some functional forms that you might have come across. Tershoff-Brenner, EAM, as I mentioned before. Here's a diamond structure to illustrate. And these potentials are reactive naturally. That's where the scientific questions are. But they're not very accurate, in the sense that the forces and energies you get out of them are very, very far from DFT or reality. DFT is a very good approximation of reality for these materials. But the problem is, these potentials therefore are fitted not to reproduce the forces most often. That's not how they judge, but whether they reproduce some of the science that you care about, melting points, point defect energetics, and so on. And there's a long history of doing science with them, even though they're not particularly accurate. The people who really know about accuracy are quantum chemists. And they are interested in taking small molecules, like a water molecule or a pair of water molecules, and computing the potential energy surface of that moderate-sized system. So, right, a pair of water molecules has 12 dimensions. So there's 6 atoms, 6 times 3, that's 18 coordinates, but rotations and translational symmetry takes away 6. So there are 12 independent degrees of freedom, and you can compute examples of the real potential energy for points in that space very, very accurately. And people have spent the last 30 years trying to come up with functions that fit that potential energy surface. Some of the names are here: Joel Bowman, Christoph Salewitz, Francesco Pesani, and they have been rather successful. So what I'm hoping is that, but they have not used the mindset of machine learning, I would say. What I'm hoping the machine learning will do is take the accuracy of these guys and enable us to make models of perhaps organic biomolecular molecules and for reactive solid-state systems, but with an accuracy that's similar to what the quantum chemists have achieved for small molecules. So in order to make progress, many people in this field, not everyone, but many people have focused on short-range interactions. And that is because the long-range interactions that you get in materials, Coulomb and van der Waals interactions, have very good analytic models. There is, especially in the last 10 years, people have understood how to compute van der Waals interactions, how to compute good polarizabilities from which you can get good Coulomb interactions to describe long range. The real difficulty has been coming up with the short range part, the bonded interactions, the quantum mechanical interactions that give rise to different bond orders for single bonds, double bonds, triple bonds, breaking different hybridizations in carbon, for example. And so it seems fitting to split these things that we know, because there are very good existing potentials, or we have analytic functional forms, and add to them something that is short range, but depends on all the neighbors in a very complicated way, all the neighbors of an atom. And so the goal is to, after having done this split, and this split may be implicit, maybe I take a material as my first examples that do not have long-range interactions, or not very strong ones anyway, and then all that's left with are the short-range ones, and I want to approach the Born-Oppenheimer potential energy surface, all the electrons in the ground state. And because we want to be systematic, we're interested in convergence, of course, with a cost trade-off. So here are the ingredients of a potential, and I've alluded to this before. So there's a representation of the atomic neighborhood. I want the energy of an atom. I want to write the total energy as a sum of atomic energies. That's what it means. That's what will give me the speed and parallelizability. But how do I represent the neighborhood of an atom? How do I interpolate functions in that representation? And finally, what database do I take to which I can fit the free parameters? And here are the properties that I want. So from the representation, I want it to be smooth. As I change atomic positions, total energies change very slowly, so I want the representation to change very slowly. I want it to be faithful. I'll talk more about that in a little bit, but that means that only two configurations should give rise to the same representation, only if they are the same. Two neighborhoods should only give the same representation if they're genuinely the same, up to symmetries of permutation and rotation. And I want these representations to be continuous. So if you change the number of neighbors, if I have a reaction, I don't want any discontinuities. Interpolation should be flexible, of course, because I don't know what the potential energy surface really is. But again, it needs to remain smooth and have hopefully very few and sensible human adjustable parameters. But then the real quagmire will come when we come to the database. So how do we select what configurations to fit to? And this is where machine learning really presents new problems that we have not seen before. This is not a big problem for simple parametric potentials, but it's a very big problem for machine learned potentials. Okay, so just to get a little bit more mathematical, the way we fit a simple function like a pair potential is that you write the total energy as a sum of a function. I'll call it V2, so a pair potential. It has some parameters alpha and beta, and it depends on the distances between atoms j and j prime. And we go into sum over all pairs. So if you get yourself a few example configurations, let's say you compute some total energies with DFT, then you can write an equation which is the total energies on the left, your ansatz for a given alpha and beta on the right, and then you have a number of these, and you try to make them equal. And you can do that by optimization. Okay, so you're looking for the alpha and beta that minimize the square difference between the real energy and the energy that you're getting. And sometimes you might have more than one alpha and beta that achieves that minimum, so you may want to regularize your solution. So amongst those alphas and betas, choose the ones, for example, which have the smallest norm. And this is a great idea, this whole scheme, if the functional form is good enough for your purposes, if the accuracy you can reach is sufficient. The nonlinearity is in the functional form, usually. It's physically intuitive, so Leonard-Jones looks like this, and at close range it's repulsive, at far range it's attractive. That's very physical. The space is very low dimensional, the search space. Alpha and beta are just two parameters that you're trying to fit. And it's very easy to get enough data. You don't need very many of these equations to nail down alpha and beta. Maybe a few dozen, or maybe two, if you choose them well. So, and both of these things imply that these potentials have what I call good transferability or extrapolation properties. And the way I think about that is that this functional form extends over all possible pair distances that you're ever likely to encounter. A fit like this is not going to fail by running a simulation and suddenly finding a pair distance which the training has never seen. It's somehow out of your scope, and so the function there is wrong because of that. Right? So if a typical material will have distances between 1 angstrom and, say, your cutoff is 6 because the interaction goes to 0 there, and everything between 1 and 6 you can sample, no problem. The problem is accuracy, is that this function just doesn't have the capability of matching the real thing, but it's not a problem of extrapolation. This will change when we go to machine learning. It'll just go the other way around. We can represent any function with machine learning, but in a high-dimensional space, we will have the problem of extrapolation. So, how do machine learners fit functions? Now the space, I want to fit functions in high-dimensional spaces. So let's think about a space X in which I get samples Y, I get these pairs, and I'm going to fit them not using a function with nonlinear parameters, but using a nonlinear function K with linear coefficients. So imagine that K is a Gaussian. It doesn't have to be, and it won't be in many parts of this talk, but will be in some parts of the proceedings. So imagine that K is a Gaussian, and I fit the function as a sum of Gaussians, and my degrees of freedom are alpha, the magnitude of those Gaussians. And I set the width. We'll talk about how to do that later, but the width is fixed. And the function for any new X is a sum over a whole bunch of X points, which are typically samples that you've seen before, and these Gaussians are centered on data points that I've seen before, and K measures essentially the distance from the old data to the new data with a Gaussian decrease, and I sum over them all to get the function. And how do we get the coefficients? It's not a problem of optimization, it's just a problem of linear algebra, because you plug in the data Y, you plug in the x's that you have, and you want this equation to be as true as possible. And that's a problem of, that's just a problem of matrix inversion, right? The matrix is that this linear system is very often very ill-conditioned, so we find ourselves adding a diagonal to the matrix. This is the matrix form. So the vector y contains all my data. The matrix K is what we're going to call the kernel function, but it's really the evaluation of this basis function at all pairs of data points. Here's my linear diagonal that I'm adding, and alpha are my coefficients. It's just a rewriting of this equation for all the data points. And in order to get alpha, I just invert this K plus sigma matrix. And that's what everyone does. That's machine learning on one slide. The functional form that you get out of this, in the end, is just plugging back the alpha into this. Is basically C inverse y is the alpha, and it's a dot product between that and this kernel vector, which is the evaluation of your basis functions at the data point, at the new point x that you're asking what the function is. So some remarks about this in contrast to the previous way of fitting functions. The nonlinearity is now in K, and that is a basis of a linear fit. And this is called, this idea has a name. It's called the kernel trick. So that you're doing a very high-dimensional linear fit rather than a low-dimensional nonlinear fit. Okay, so the dimension of the space in which you're doing the linear fit changes. If I get more data points, I can dramatically increase the number of degrees of freedom. And that, again, is a deep idea that the more data I have, the more degrees of freedom I have in order to fit the function. And it's hard to get enough data to fill space. So it's very hard to get so much data that you get data from everywhere, that your function that you have basis functions everywhere where you will ever want to be, where you will ever want to evaluate the function. So you get very poor extrapolation, poor transferability with this method, and that's what that's what we're fighting with when we make machine learning fits. Here's a 1D example. So here's the one-dimensional function I'm trying to fit, and I get data points at these green crosses, and each of the red curves is a Gaussian centered on one of the green crosses, the location of the green crosses, and I've drawn them in proportion. So if you add up all the red curves, you get the green curve. And it matches with the target blue curve very, very accurately. This is what machine learning looks like up close, but in very high dimension, which is very hard to think about. I'm not going to dwell too much more in the mathematics of this fit. There is a lot more mathematics here. I just want to point out that when people think about what kind of basis functions to use, so these are the questions. How do we transform the coordinates? That's the problem of representation. What kind of kernels we use, and how we get data. But the kernel choice is sort of, I think about it in this way. So think about what the potential energy could look like. It should look like this. It shouldn't look like this. And there is a way, which my 1 hour doesn't allow me to get into, which kind of uses this probabilistic idea in function space to say that I want to assign high probability of finding functions like this and low probability to finding functions like this. And if you go through that mathematics, you discover that that statement of what is high probability function and what is a low probability function is related to the kernel. So that basis function that we use to build up our approximation is sort of intimately related to what we think are high probability functions. And so here's an example of this. Suppose this is the kind of function I want, and here's a point which I know about. And here's another point. Then if you think about a probability of what this point could be, or let's take this point as the one that's given, and this is the one that I'm uncertain about. And if I imagine a probability distribution around some value, then and I imagine that probability distribution changes as I separate these 2 points. So now we're talking about the distance of points in the input space, and if we think about probability distributions of the values of the function as a function of that distance, it turns out that that probability distribution is equivalent to the kernel. So a Gaussian kernel that I've shown before, which used to be just a basis function, can be recast as a probability of finding a point, a value, as a function of distance away from other known values. I'm going to leave it at that, but you can find in textbooks and literature a much more rigorous connection between basis functions and probabilities. So the sort of summary of this Gaussian process regression really comes from this probabilistic way of looking at things, and what it also what it gives us, and this is in a longer talk I would have gone through the maths of that, but what it tells us is it gives us interpretations for some of these parameters in the kernel that we use as basis functions. So it turns out that this sigma here, which is the width of the Gaussian, is the probability, is a measure of length scale and how far we go away in input space and how far we have to go until the function becomes uncorrelated with a previous value. And so in potential energies of atoms, this sigma is essentially 1 Bohr. So it's the atomic radius. It's the radius, it's the distance over which atoms really strongly affect one another. This other, for example, this other value, which is the diagonal, the one that used to just look like a little trick to enable us to invert a matrix, it turns out to correspond to the noise of the measurements, the accuracy with which I'm able to determine the function values given a position. So all of these are actually very physical numbers for which we have very good ideas, and in my own work I typically don't optimize them as some other people do. I declare them. I declare sigma to be 1 Bohr. I declare this sigma nu to be a milli eV per angstrom, which is about the accuracy with which these potentials can capture DFT. I'm going to skip over a 2D example because I don't think it adds that much to the talk. I want to get back to the main flow. So the machine learning framework that I've outlined, this high-dimensional fitting with linear basis functions, actually encompasses a lot of ways of fitting. So linear regression, which is a well-known statistical technique, is just the same thing if you take this kernel function to be the dot product, a very, very simple kernel function, right? And that is because if k is, let's just, q is my representation now, could be atomic coordinates, could be something else, but if k, qi, qk is just qi dot qk, then I can swap the sum that's implicit in this dot product with this sum, and you end up with the function being just the representation dotted into a set of constants. Those are your linear coefficients. Neural networks, which you will have heard about if you hear about machine learning and material science, some simple neural networks, specifically the ones with a single hidden layer, can also be cast into this form. And with the kernel given by this function, they're equivalent. They can do the same thing. Deeper neural networks with more layers don't have a simple kernel like this, but one can still relate them. I'll show that to you on the next slide. Gaussian kernel is what I've talked about before. As I mentioned, the crux of the matter from now on is what are the descriptors, what kernel do we use, and how we pick the database. Actually, there are two things in database choosing. What data do we generate with DFT? But also, this sum very often should not range over my entire data set. There is not necessary, in fact it is detrimental to put a basis function on every single data location that you obtain. You can get away with many, many, many fewer basis functions, 100 times fewer basis functions. How you pick them is something that is that people actively think about. A comment about deep neural networks. So you can think of what I've shown you as linear algebra, basically taking some basis function in some space that we need to carefully think about, and just adding them up as a sum to produce my function. That's what I showed you before. Deep neural networks basically start with some representations, start with some simple functions, but then add them up in a nonlinear way to come up with new basis functions, which are then at the second or third layer of an artificial neural network are combined again, summed up through a nonlinear function, and finally you add them up to get your function that you want. So you can think of deep neural networks as a way of adapting basis functions with which then you sum them to make the function. And deep neural networks have had a huge success, especially not in material science, in situations where we have no idea what the right basis functions are. So for face recognition, what are the right basis functions in the space of pixels? Nobody knows. So deep neural networks come to the rescue and construct the right basis functions. I'm going to argue that in material science, we actually do know a lot about basis functions, and we can find analytic basis functions that are very, very good. And I have not yet seen a neural network that outperforms handcrafted basis functions. That could change. So it's possible that there'll be a limit when neural networks constructed basis functions are better. But of course, when you use a neural network, you buy yourself a very hard optimization problem. So training the neural network becomes a sort of dark art. Okay, so now I want to show you examples. And the first example is a very simple one of just the water timer, because it's a very old example. Very many people have potentials for a water timer, but it illustrates very nicely what you actually need to use one of these machine learning methods in a sort of very, in a mathematically simple way. So we're going to use the representation of just the intraatomic distances, but not their unordered list, the ordered list of intraatomic distances. So basically, we know in the database we have the atoms in a specified order, and I have the 15 intraatomic distances, knowing which one connects which pairs of atoms. I said before this was a 12-dimensional space. I'm going to use 15 dimensions. That's okay. So high-dimensional fits are extremely tolerant of throwing in a few extra dimensions. What I gain by doing that is a lot of symmetry, right? So it's very simple to construct this input space. The potential energy function is invariant to permutations. And the way the Gaussian process regression enables you to encode that is that I can take my kernel, which is going to be a Gaussian in this 15-dimensional space, and I can sum that up over the permutation group. So there's 8 ways to permute atoms to get back to the same pair of molecules, and we can take the sum over the 8 permutations of the kernel to get a new kernel. And that's now not a Gaussian. It's a complicated sum of specific Gaussians is my basis. So I just wonder, here's how hard this problem is to fit the potential energy of a pair of water molecules. Here's the near exact answer, the black one. That's my exact answer. That's I mentioned my quantum chemist friends. That's the cheapo, inaccurate method for them. But for us, for this purpose, it's going to be almost the exact answer. All the other curves here are various DFT functionals. And the points are energies of water hexamers. So these are different combinations of 6 water molecules, and what the exact answer, all these energies are correspond. One point corresponds to one of these hexamers, and DFTs are all over the place. What we see here is if you take the pairs, the dimers out of all these hexamers, you take a lot of them, not just these 8, but very many, and then these are the errors of DFT, of the blip functional. So this is the blue points are errors of blip. Blip plus D, so this is Grimmett correction, I think D2 gives you the black points. It's just the energies of the water dimers. So if you take the machine learning fit, then on the same scale, you get the blue curve. So very, very, very accurate. So these are all sort of machine learning fits, although not everyone calls them that. The green one is Joel Bowman's quantum chemistry late 1990s fit. It's as good as the best DFTs, but not that good compared to modern standards. MB Pol is Francesco Pesani's, so the red one is Francesco Pesani's fit, much, much better than WHBB, and the blue one is our fit. So you can use this method to get accuracies for water dimers, and these are for the hexamers where you add up all the dimers that are in the hexamer, and you can get very, very accurate fits with this. Yeah. So if you want to build a potential for materials, however, you have to do something more complicated. Imagine that I have amorphous carbon here. I want to describe it from the low density phase up to the high density phase. Lots of bonds are going to break as I progress through there. This is the representation that we've used before. So the interatomic distances are, if I have an atom and they take all its neighbors, and you take the dot product between all the neighbor vectors, that's the all interatomic distances of all the atoms within this region. The problem with that representation, which is fine for the water molecule, water dimer, the problem is that it's not permutationally invariant, and for a carbon with 20 neighbors, I can no longer sum over the permutations. That would be 20 factorial sum. That's too expensive. And a fixed number of neighbors in this representation. It's very hard to do reactions. So let me show you our solution to that, and that's the SOAP descriptor, or rather the SOAP kernel. Descriptors and kernels become one in this formulation. So I'll show you that, and then I'll show you examples of what it can do. So we take a completely different approach. Rather than think about interatomic distances, we take a central atom, and we take all its neighbors and put a Gaussian on each. And we call the sum of those the neighbor density. So it's not electron density, it's a sum of atomic densities, and this sigma here is the width of that Gaussian, and it's one Bohr. So then we take that, and in order to construct a kernel, I take the overlap. That's the kernel is a basis function that compares two environments. So it's a function that gives me a scalar given two of these environments. And if I have two of these environments, I integrate them in space. Okay, so that's the overlap integral. But that is not rotationally invariant, although it is permutationally invariant. But it turns out that if you square that and integrate it over all rotations of one of the environments, that's a rotationally invariant kernel. So the full formula is this: integrate the densities, and then integrate them, square it, and then integrate them around all rotations. That would be very expensive if you had to do it explicitly, but we don't. If we expand this neighbor density in YLMs, spherical harmonics, so C and LM are the expansion coefficients, it turns out that this overlap, rotationally integrated overlap, is exactly equal to the dot product of what we call power spectra, which are just dot products of the spherical harmonic expansions. So parts of this algebra was known. The diagonal parts of this P are the same as Steinhardt bond order parameters discovered decades earlier. But the full equivalence of this P dot P to this integrated overlap is a new piece of mathematics. And very often, almost always when we use it to fit, we actually square this kernel, and that's the kernel that we use. The human-controlled parameters are this exponent, which is 2, this sigma, which is 1 Bohr, and this cutoff, right? The region within which I take my neighbors. And that is about 5 or 6 angstroms. So I'm going to skip over a few of the details, but then I'm going to show you some examples. So the first one is tungsten. People are very interested in tungsten potentials because they want to model in the interior of fusion devices. So we build a database, and the database is complicated. So it has primitive unit cells, large bulk unit cells of BCC tungsten, vacancies, gamma surfaces of vacancies, and so on. Here are some tests of phonon spectra, elastic constants, vacancy formation energies. And here are 6 potentials, each one containing all the database of the same line and above. And the green parts are, green squares show good performance. So what you see is that if I add more data, I get good performance across a range of properties. Here's another way of looking at the accuracy. So here are percentage errors with respect to DFT of a few existing potentials that span about 3 decades of materials modeling. It's not very good. When we make the gap fit, you get all properties right. And this, again, isn't surprising because machine learning works, Gaussian process regression works. What is more surprising is that these potentials are now stable and you can do molecular dynamics with them, that this database is sufficient to do the science that you want. I want to show you one more example, and that's going to be, we can do the same for iron. Let me skip that. I want to show you the carbon example. So in the tungsten case, we sort of went for cold tungsten, defects, high accuracy for point defects, surfaces, and so on, and sort of build up the potential from below. If you take that model and run it at 10,000 Kelvin, it's not going to be very good. No liquid configurations were in the database. In amorphous carbon, we tried the other way around. So now we have our descriptor fixed, our interpolation scheme, the sum of basis functions, linear sum basis function fixed. Really, it's about exploration of database building. So can we build a database for carbon that is never very stupid? It can give you reasonable energies and forces for carbon structures at all range of all kinds of densities that you'd want. And amorphous carbon is a very difficult example. It has very many different kinds of bonding. Densities vary a lot and so on. So here's the protocol. So we take amorphous carbon and we melt it at 9,000 degrees, and then we hold it at 5,000 degrees, and then we quench it and anneal it to form amorphous carbon. And we do that at a range of densities. And so it looks like this for the low density part. And here's what we get. So if we use just a two-body potential to fit the resulting data, you get these sort of green dots. This is an energy-energy correlation plot. This is a force-force correlation plot. These are errors corresponding to the same quantity. And this gray cloud shows you that pair potentials really do a very, very poor job. If you turn on three-body potentials, then you get the black dots, which is a very big improvement. And you can see in the errors that a lot of the errors are really now down here. And now we turn on the SOAP kernel, the many-body kernel, and you get still a further improvement. It doesn't look like a huge improvement, but there's still an improvement. The interesting thing is that if you take the 2 plus 3 body potential, it's not actually a very good potential. You can't do a lot of science with it. But if this extra improvement that we get from the many-body kernel, the SOAP kernel, is good enough to actually then produce very good properties of amorphous carbon, which you don't get if you just use a three-body potential. So here are the sort of examples that we want. So here's the Young's modulus, which is a simple property for a crystal, a very complicated property for an amorphous material. Because as you pull the material from one side, everything relaxes in unpredictable ways. So here's the experimental data of the little colored triangles. The best potential out there, analytic potential, is this black one, and we get this red curve here. And you don't get it if you don't use the many-body potential. Here's the same thing for surface energy. So you quench one of these amorphous carbon structures, then you break open a surface, and you measure the surface energy, and we're spot on with DFT, even though there were no surfaces in the database, and the best potential is far off. So I think it's best to stop here. I'm very happy to answer questions, and you'll hear more of the same from the next talk.